Hello and welcome to this presentation of ViewNeRF, unsupervised viewpoint estimation using category-level neural radiance fields. I am Octave, and in this video I will quickly walk you through the perks of our model. We will be discussing ViewNeRF, a method to recover viewpoints for an object category without any labels. ViewNeRF is based on neural radiance fields, a recent family of 3D reconstruction models able to produce realistic reconstructions which it uses for strong and efficient real data predictions. The original NeRF model requires ground truth camera poses during training. Since then, a variety of pose-free NeRF-inspired models have been proposed. However, these suffer from heavy limitations. Like the original NeRF, these are designed to reconstruct only a single scene at once. Therefore, they are unable to generalize to new object instances. They use a gradient-based pose optimization process, meaning they only learn the pose for training views. Some work have shown ability to recover poses for unseen views after training, but the process involves performing many backpropagation passes to the NeRF model, which is expensive and can get trapped in local minima. Finally, all but one of these methods can only operate unsupervised in forward-facing scenes, in which all camera poses are similar. In the more challenging setting, where cameras span the full 360 degrees of rotation around the object, these methods are unable to converge to proper 3D modeling of the scene, which translates to poor pose estimation results. We propose to address these issues by using an analysis by synthesis approach. Multiple methods have been recently proposed to disentangle viewpoint and appearance of objects in images by using a reconstruction objective, coupled with two pipelines, a pose predictor and a global appearance encoder. Both predictions are combined to obtain a faithful reconstruction. However, these have only been proposed with relatively simple 3D reconstruction processes like voxels, point clouds, or meshes. In practice, this limits their training to synthetic datasets like ShapeNet. In comparison, NeRF allows our approach to be trained directly on real images thanks to its powerful rendering scheme. Let's have a look at how our model differs from existing neural radiance fields. In standard NeRF, the model attempts to learn a single 3D scene. For each training image, a ground truth camera pose is used to sample rays corresponding to specific pixels. The NeRF neural network is then queried multiple times along the ray, and a volumetric rendering gives a predicted pixel. This can then be compared with the target image, providing the supervision signal. In pose-free NeRF, like NeRF or self-calibrating NeRF, the pose for each training image is now treated as an additional model parameter that is jointly optimized during training. As mentioned earlier, this suffers from three limitations, which are the ability to only model a single scene, no convenient inference strategy for viewpoint estimation, and in general, failure to converge if poses distribution is complex. Fairly related to our approach is CodeNeRF, which allows to model multiple objects in a category by introducing a conditioning mechanism based on instance-specific codes. However, it is trained with ground truth camera poses and uses learnable object codes, making inference a complex task. Our model instead proposes to train two neural networks to predict the pose and the appearance of an object from a single image pair, and uses these to train a conditional NeRF model similar to CodeNeRF. These auxiliary models can then be queried on unseen objects or viewpoints for inference purposes. Additionally, to allow ViewNeRF to operate on 360-degree scenes, we introduce a pose regularization scheme. When working without ground truth cameras, pose-free NeRF must solve the challenging problem of joint optimization of pose and appearance. A reconstruction error can be caused by imprecise camera pose, or by improper modeling of the scene by the object code or the NeRF's neural network. Disentangling these factors can be complex, and in practice it leads to pose collapse, where camera poses are all predicted in the same region of space. The model then tries to compensate by overusing NeRF's powerful rendering scheme, causing degenerate solution as illustrated on this video. The figure on the right shows such a case, where the model predictions in orange are concentrated on the right side, whereas ground truth poses span a full 360 degrees rotation. The green lines represent matching between ground truth and predictions. It can be seen that for some of them, the distance is small, but for others, it is extremely large. In forward-facing scenes, this is only a minor issue, as poses are indeed concentrated in a single region of space, but it is a major concern on 360-degree scenes. Ideally, we would like our model to be able to predict any possible viewpoint around the object, that is, any point on the blue sphere. Our pose regularization scheme consists in randomly drawing pseudo-targets from the expected distribution and assigning each of these to its closest match in a batch of predicted poses. The distance between each prediction and its pseudo-target is then added to the loss of the model. This encourages the predictions to spread and cover as much of the possible poses as possible. Of course, these pseudo-targets have no guarantee to be anywhere close to ground truth poses. Therefore, the regularization is progressively tuned down before being completely disabled once the collapse has been avoided. We evaluate ViewNeRF's pose prediction capabilities on two datasets: ShapeNet, which consists of multiple renderings of 3D models, in our case cars and chairs, and FarbeCar, a dataset of real views from 47 different cars. The viewpoint on both datasets span the full 360 degrees of rotations around the object. We compare our model against CodeNeRF that we introduced earlier and ViewNet, a voxel-based analysis by synthesis approach that also performs unsupervised viewpoint estimation. Reconstructions during inference show that CodeNeRF, despite being supervised, struggles to produce good images when it is not given a good estimate for the pose. That is because of the difficulty of jointly estimating for pose and appearance. When initializing the process from a nearby pose, it converges properly to a much more convincing image. While both ViewNet and ViewNeRF produce decent-looking reconstructions, although some details can be missing, like the black strip on the hood of the car. CodeNeRF's convergence issue is further illustrated on the quantitative results, where it barely manages to go beyond random performances when not given an initialization, and is even beaten with initializations on ShapeNet chairs. Compared to the voxel-based ViewNet, which is also an unsupervised approach, ViewNeRF seems to have only marginal improvement. This is, however, not the case anymore when training these models on real data. As shown in these reconstructions, voxels seem too limited to model the complex patterns of real data, while ViewNeRF can capture model-dependent appearance changes thanks to its NeRF backbone. This translates to a much larger performance boost, yielding a 25% increase in accuracy and 20% decrease in median angular error. Finally, compared with gradient-based pose recovery, analysis by synthesis models are much more efficient, with inference processing times being 5 orders of magnitude faster. ViewNeRF extends pose-free NeRF models by focusing on 3 improvements: category-wise pose estimation capabilities thanks to a conditional NeRF model, faster and more general inference granted by prediction networks for pose and appearance, and 360 degrees capabilities for which a pose regularization scheme is designed. Compared to other analysis by synthesis approaches, ViewNeRF shows much stronger results on real data thanks to the capabilities of the NeRF backbone.